Here we have a hanging mass, which is only 5 kilograms, connected via a pulley to a mass on a table, and the table's frictionless. So when we release this system, the hanging mass is going to fall, and because there's no friction acting on the 40 kilogram mass, it's going to cause the system to rotate clockwise. So let's start by labeling our forces. So I've got my 40 kilogram mass. Obviously there's a force of gravity straight down, a fairly significant one because it's a fairly large mass. I'm going to call that mass 1, so label it Fg1. Now because it's on a surface, there's a normal force that would be equal and opposite. Now I know it's equal because we know this 40 kilogram mass is not going to move up or down. It's only going to move horizontally. So there is no net force vertically. So I've got a normal force I'll call Fn1, which is exactly equal to Fg1. They're going to cancel each other. Now as for the forces that are actually driving the system, I'll do those in pink. Starting with the 5 kilogram mass, there is a force of gravity acting down on it. I'll call that Fg2. Not as big as Fg1 because it's a smaller mass, but it's enough to overcome the inertia of that 40 kilogram object. Now what's preventing this thing from falling at 9.8? Well, the rope. Same rope, so it should be the same tension on both sides. Ropes always pull, so there is a tension force holding mass 2 up. I'll just label it T. Now because it's the same rope, there's also an equal tension force pulling mass 1 to the right. So it'll be the same length, like that. So those pink forces are all parallel to the motion of this system. We know that this system is going to kind of go like this around the corner. That's going to be the direction of my acceleration. So all we care about are forces that are contributing in that direction. Certainly Fg2 is, T is, and this T is as well. So now when I look at the entire system and come up with my equation of motion, I get F net, which is the sum of forces, will be, it doesn't matter what order I do it in, this tension will be positive because it's going in the direction of my acceleration. This tension will be negative because remember the 5 kilogram mass is falling, so this is going against the acceleration, so minus. And then Fg2 is positive because it's going in the direction of the acceleration. Notice that the tensions cancel once again. The green vectors don't go into my equation because for 2 reasons. 1, they cancel each other off. And 2, they're not in the direction of motion. There's no component of them that's parallel to the acceleration. So my net force is always ma. And because I use the entire system, this would be my total mass. ma is going to simply be equal to Fg2, which is m2 times g. So my acceleration will be m2g over my total mass, which is simply 5 times 9.8 all over my total mass, which is 5 plus 40, 45, and I end up getting an acceleration of 1.1 meters per second squared. Keep in mind for any of these pulley problems, you can't get an acceleration greater than 9.8 because gravity is driving the system. So now we know the acceleration. Now if I want to solve for the tension, I have to now isolate either the 5 kilogram mass or the 40. Now remember, the green vectors have canceled. So pick the mass that's easier to solve for T. 40 kilogram mass looks much easier because there's only one force attached to it in the direction of motion. So I'll use blue for this one. So if I look at just the 40 kilogram mass, isolate, I get F net equals, so remember, I'm just looking at this guy, ignoring the rest of the pulley system. The only force that's acting in the direction of motion is tension. So F net is ma. So to solve for T, I just need to know the mass and the acceleration. Well, it's mass 1, because that's the mass I isolated. We know the acceleration. And I end up getting a tension of 44 newtons. Now, if you have time, quickly check it with the other mass. I'll do the other mass in yellow. So if I look at the 5 kilogram mass and just isolate it, I get F net equals, now Fg2 is positive because remember it's falling, that's the one in the direction of the acceleration, minus T. So my tension will be Fg2 minus Fnet, which is M2G minus MA. Fnet's always MA, and because I'm using mass 2 only, M2A. So if you work this one out, you should get 5 times 9.8 minus 5 times 1.1, and you end up getting 44 newtons as well. So obviously the mass on the table was a little easier, but both are fairly straightforward, and it's nice to confirm that the tension is the same for both.